All right, hi everybody. Welcome to the seminar. Today we are happy to have AJ Boo from Rutgers University, who will talk to us about enumerating restricted Dyck paths with context-free grammars.
All right, yeah. So I'm going to be talking about a paper that I co-wrote with Robert Dougherty-Bliss. That has, the title was Enumerating Restricted Dyck Paths with Context-Free Grammars. So I'm going to start off by just going over a couple of the basic definitions of that are relevant to the paper. So a Dyck path of semilength n is a list of n positive ones and n negative ones whose partial sums are always non-negative. So if we wanted to find the set of Dyck paths of semilength 3, we could use a Mabel package written by Doron Zeilberger, which can be found on his website. It's called dyck.txt, and it outputs the following set, right? And looking at this, as we can see, this is the number of ways, this is all of the ways that we can list 3 positive ones and 3 negative ones, such that at any point there are at least as many positive ones as negative ones leading up to it. Okay, and so we refer to the positive ones as an up step, which we denote with the letter U, and the negative ones as a down step, which we denote with the letter D. And the height of a path at position K is the sum of the first K elements of that list. So going back to our definition, another way to think about this is basically a Dyck path contains ups, like you can either step up one or step down one, and you know that you're never going to have a negative height and that you're going to start and end at height 0. So this is an example of a Dyck path of semilength 2, right? Because we have 2 up steps and 2 down steps. And here we're stepping up to height 1, down to height 0, up to height 1, and then back down to height 0. This is an example of a Dyck path of semilength 3, but here we're stepping up to height 1, then up to height 2, down to height 1, back up to height 2, down to height 1, and down to height 0. So these are 2 examples of Dyck paths. This path, however, it would not be a Dyck path, right? Because we can see at position 3, we had just stepped down to a negative height. So it's not going to be a Dyck path. Similarly, this path, UUD, is not a Dyck path because we can see that we're ending at height 1 instead of height 0. Okay, so now that we know what Dyck paths are, a natural question to ask is how many Dyck paths are there of semilength n? And to enumerate the Dyck paths for all such n, we use the weight enumerator. P of x equals the sum from n equals 0 to infinity of r of n times x to the n, where r of n is the number of Dyck paths of semilength n. And we can solve for our p of x if we first recognize that p of x is equal to 1 plus x p squared of x. And in order to do that, we can prove it grammatically. And these sorts of proofs are the type of proofs that we focus on in our paper. So if we let P denote the set of all Dyck paths, then P satisfies the grammar P equals the empty path union UP-DP. So what we're saying here is that any Dyck path is either going to be the empty path, or we know that it has to start with an up step, right? Because if we started with a down step, we'd immediately be at a negative height and we would immediately know this is not a Dyck path. And then we know that at some point, we're going to have to return to height 0 for the first time, right? Since we end at height 0, we know that we have to get back there. But something could happen in between those up and down steps, and then something can happen after that down step, right? Because we can return to 0 multiple times. But because of the way that we define that down step, we know that whatever happens here has to start and end at height 1, and it can't ever go to height 0. So therefore, this subpath must also be a Dyck path. Similarly, this subpath also must be a Dyck path, right? Because if it ever goes, we know that it has to end at height 0 because our overall path must end at height 0. And if it ever hits a negative height, then our overall path also hits a negative height. So that's how we know that our family has to satisfy this grammar. And these are obviously disjoint because one of them is the empty path and one of them is clearly non-empty. Like it has an up and down step at least. Okay, and then we can use the counting function to translate this into p of x equals 1 plus xp squared of x. So we're taking every occurrence of p and subbing it with p of x, and then the empty path has semi-length 0 because it's empty, so that becomes 1, and then the u and d that has semi-length 1, so it becomes the x. Okay, and then we can solve for our p of x, and we get p of x equals 1 plus or minus the square root of 1 minus 4x over 2x. And we need to figure out which one of the two of these this is. And since we know that there is exactly one Dyck path of semi-length 0, namely the empty path, we know that if we take the limit as x goes to 0, we want to get 1 for the right answer. So if we do this and take the limit as x goes to 0, both of these, one of them gives us infinity, the other one gives us 1, and so that we know then that p of x must be 1 minus the square root of 1 minus 4x over 2x. Okay, and then we can use Newton's binomial theorem to rewrite this, and so we get p of x can be written as this power series, and this is going to show up on the next slide, so I'm just going to go to that. Okay, and then we know that the number of Dyck paths of semi-length n has to be the coefficient of our x to the n, right? Because this is the weight enumerator, and so that's what we defined it to be as. And then we can rewrite that coefficient as 1 over n plus 1 times 2n choose n, and this is going to give us the nth Catalan number. And indeed, if we generate the first 12 elements of the sequence enumerating Dyck paths of semi-length n, we get the first 12 Catalan numbers. Okay, so in our paper, we are particularly interested in looking at restricted Dyck paths, and so I'm going to define the specific restrictions that we looked at. So a Dyck path has a peak at height h if it contains a bigram ud such that the height of the path after u is h. So basically, right, if it has an up step followed by a down step such that right there, after that up step, we're at height h. Similarly, it has a valley at height h if it contains a down step, which is immediately followed by an up step, such that the height of the path after that down step is h. So looking at this Dyck path, if we want to find the peak heights, we would see that there's a peak right here, which has height 2. There's a peak right here that has height 3, and a peak here that also has height 3. So the peak heights for this Dyck path are going to be 2 and 3. And then if we wanted to look at the valley heights, right, we would see that there's a valley right here that has height 1, and another valley right here that has height 2. So this path has valley heights at 1 and 2. Okay, now given a sequence of steps L, we're going to let L to the n denote the repetition of L n times, right? So for example, u cubed would be 3 up steps, u, and like ud squared would denote up, down, up, down. Okay, so then the other restrictions that we looked at are, so if a Dyck path has an uprun of length n, then it contains at least one u to the n that is not directly preceded nor followed by a u. So it has a run of exactly n up steps. And similarly, it has a down run of length n if it contains at least one d to the n that is not directly preceded nor followed by a d. So going back to our example up here, right, we can rewrite our Dyck path as u squared d u squared d u d cubed, right? And so we know that our uprun lengths are going to be 2 and 1, and our down run lengths are going to be 1 and 3. Okay, so those are the restrictions that we looked at. And previous findings which motivated our paper include a paper published by Doron Zeilberger, which was titled Automatic Counting of Restricted Dyck Paths via Numeric and Symbolic Dynamic Programming. And it was accompanied by two Maple packages, dyck.txt and dyckclever.txt, which were able to find the polynomial equation satisfied by the weight enumerator of the set P of A, B, C, D of Dyck paths avoiding peak heights in A, valley heights in B, upward runs with lengths in C, and downward runs with lengths in D. These programs, however, were limited to finding the generating functions for a specific set of restrictions. So, for example, it could find it for the set of Dyck paths avoiding peak heights in 2r plus 1, where r is some natural number. But they also use more complicated proofs. So if they wanted to solve for the polynomial equation of a family of Dyck paths that have both restrictions on peak and valley heights as well as upward runs and downward runs, then the only way that the program could do this is by generating sufficiently many terms of the sequence, enumerating the Dyck paths with this set of restrictions, and then solving for the polynomial after. If, however, we're only looking at restrictions in peak heights or valley heights, or peak heights and valley heights, or upward runs and downward runs, then it's able to find the polynomial equation by generating a more complicated grammar, which involves creating a system of equation that it includes the generating functions of many different families of restricted Dyck paths, and then solving it to get the appropriate equation for the original family of Dyck paths. So it's hard to gather information because you end up with a lot, other than the output, gather information beyond the output, because you end up with like a system of equations with a bunch of different families of Dyck paths. So it's hard to see what's going on. Okay, so one thing that we proved in our paper is that the number of Dyck paths of semilength n whose peak heights avoid 2r plus 3 for r greater than or equal to 0, and whose upruns are no longer than 2 is 1 when n is equal to 0, and 2 to the n minus 1 when n is greater than or equal to 1. And so if we let P denote the set of all such Dyck paths, and Q be the set of Dyck paths avoiding peaks in 2r plus 2, and upruns longer than 2. So note that the difference between P and Q, right, is that we're switching from avoiding peak heights in 2r plus 3 to avoiding peak heights in 2r plus 2. Okay, and then we want to look at the grammars of each of these. So Q satisfies the grammar Q equals the empty path union UDQ, right? Because any element of Q is either the empty path or it has to start with exactly one upstep. Because if it starts with, if we were to have an upstep followed by another upstep, we know that we can't have an upstep after, right? Because then we would have an up run length longer than 2. But we also know that we can't have a downstep after, because then we would have a peak height at 2, which is also not allowed. So therefore, it has to start with exactly one upstep. And then something can happen after we return to height 0, but we know that whatever happens after also has to follow the restrictions that were set on Q, because any uprun in Q is going to be an uprun in the overall path. And we know that it has to be a Dyck path because we're at height 0. So we have to end at height 0 and can't go below that starting height. So Q satisfies that grammar. Oops. And then P satisfies the grammar P equals the empty path union UDP union UUDQDP. And so here, right, we're saying that any path in P is either going to be the empty path or it's going to start with exactly one upstep, in which case it has to have this grammar by the same argument that we used up here. Otherwise, it starts with exactly 2 upsteps, right? And then that has to be followed by a downstep. Otherwise, we would have an uprun of length longer than 2, which is not allowed. And then at some point, it has to return to height 0 for the first time. And then we know that something can happen here in between the 2 downsteps, and then something can happen after that last downstep that we wrote out. And again, right, because of the way that we defined our D to be the first time that we return to height 0, we know that Q has to be a Dyck path. And we know that P also has to be a Dyck path. And Any uprun in either of these are going to be upruns in the overall path, so they can't contain upruns longer than 2. And any peak in P is going to have the same height as the peak in the overall path. For Q, for this subpath right here, however, right, since we're starting at height 1, and we want to avoid peak heights in 2r plus 3 in the overall path, that means that here we actually want to avoid peaks in 2r plus 2, and that's how we know that we want this to be an element of our family Q. So that shows that any element of P that starts with an uprun of length exactly 2 can be written by that grammar, and that this grammar only produces those elements. Okay, so then we can translate these using their generating functions to the equations P equals 1 plus XP plus X squared PQ and Q equals 1 plus XQ. And then we can solve them to get Q equals 1 over 1 minus X and P is equal to 1 minus X over 1 minus 2X. And then if we look at the Taylor series for these, we would get that the coefficient of X to the 0 is and P of X is 1, and that the coefficient of X to the N for N greater than or equal to 0 is 2 to the N minus 1, which is what we wanted. So that concludes the proof of that theorem. So a similar object to Dyck paths that we're going to talk about in this next proof are Motzkin paths. And Motzkin paths are similar to Dyck paths, except for they allow for flat steps, F, that don't change the height. The nth Motzkin number, M sub n, is the number of Motzkin paths of length n, and it's known that the generating function m equals m of x for mn satisfies the equation m equals 1 plus xm plus x squared m squared. Okay, so what we want to prove is that the number of Dyck paths of semilength n, which avoid upruns of length 3 or more, equals the nth Motzkin number, m sub n. So if P is a set of such Dyck paths, then P equals the empty path union UDP union UUD PDP, right? So we either have the empty path or we start with an uprun of length exactly 1, right? And so this is how we get the UDP, and we know that it has to be that this P is in fact an element of our family, right? Because of the same argument that we used in the previous slide. Otherwise, it starts with an uprun of length exactly 2. So we know that it starts with UUD. And then again, it returns to height 0 for the first time at some point. And then something can happen in between those two down steps and something can happen after. And we know that these are both going to be Dyck paths for the reasons that we stated before. And then we know that any uprun in these two subpaths are going to be upruns in the overall path. So any path written like this is going to be a member of our family if and only if P1 and P2 are also members of our family that we're looking at. So this gives us that P equals 1 plus XP plus X squared P squared. And this is the same equation that we said was satisfied by the Motzkin generating function. And you can check that P of X is in fact equal to M of X.
Can I ask a question?
Yeah.
Is there a bijection to the Motzkin paths from these that you know of?
Not that I know of off the top of my head. All right, so now I am going to define an involution that's going to become important for the later part of this presentation. So if P is a set of all Dyck paths, then consider the involution phi from P to P, where applying phi reverses the order and the direction of the steps of its input P. So for example, phi of UUD, UUDDD is going to become UUUDDUDD, right? So if we were to draw this out, we would see that like our input was UUD, UUDDD, and what we're mapping it to is UUUDDUD, right? And so basically what you're doing with this involution is you're just like flipping the graph, right, of what it looks like. And so it's clear that any Dyck path of semilength n will be mapped to another Dyck path of semilength n, right? And any up run will be mapped to a down run, and any down run will be mapped to an up run. So, oops, I'm still in the pen mode. Okay, so the number of Dyck paths of semilength n, which avoid upward runs of length in A and downward runs of length in B, is equal to those which avoid upper runs of lengths in B and downward runs in length in A, right? Because this involution that we define creates a one-to-one correspondence between these two families of Dyck paths. Okay, so all these questions that we were trying to answer is given a family of Dyck paths P, how do we find an equation satisfied by the weight numerator P of X? And the way that we address them is trying to find a grammar that generates P, and it's better if it's a recursive grammar. Right, so we often begin with an attempt to subdivide the elements of P into multiple shorter elements of P with some steps added in. And then we want to add additional terms to accommodate corner cases. And we want to make sure that we're not like double counting anything or adding any sort of thing that wouldn't be in our original family P. And then once we do that, we can translate the grammar into an equation by replacing every set of 2k steps, which has semilength k, with x to the k, and any instance of P with P of X. So in our paper, one of the next question that we were addressing is, can we find identities on the weight enumerator functions for an infinite family of restricted Dyck paths? So for example, we want to look at the Dyck paths avoiding upruns with lengths in an AR plus B, where R spans over the natural numbers, for arbitrary A and B. So we said before that like Zeilberger's maple package could do this for like specific integers A and B, but not for the arbitrary case. So what we did was we presented identities on infinite families of restricted Dyck paths, and then we constructed grammatical proofs to show that these identities do in fact hold. And to do this, what we did was we tried to find a pattern by running code multiple times. So we used Zeilberger's maple package for multiple cases, and then looking at all the outputs that we got, we tried to find patterns in the infinite families. And then looking at those patterns, right, we try to come up with a grammar that matched it, that also made sense for the family. And then we try to prove these grammars using inclusion-exclusion. Okay, so an example of how we did this. So for the case where we were looking at the set of Dyck paths avoiding upruns with lengths in AR plus B, where B is less than A, and they're arbitrary non-negative integers, we would use the maple package. And for the set of Dyck paths avoiding upruns in length 2R plus 1, we got that the generating function satisfied the equation P equals x squared P cubed plus 1. And then if we were avoiding upruns of length 3R plus 1, we got P equals x cubed P to the 4th plus x squared P squared plus 1. Avoiding upruns of length 4R plus 1, we got the output P equals x to the 4th P to the 5th plus x cubed P cubed plus x squared P squared plus 1. And those avoiding upruns of length 4R plus 2 gave us the output P equals x to the 4th P to the 5th plus x cubed P cubed plus xp plus 1. Right, so then we look at all these outputs and try to find some sort of pattern. So if you look at these terms that I'm underlining, we would see like they all have the form x to the I, p to the I, right? And we note that I can be as little as 0, and that I is never greater than a minus 1, right? So like x squared, when our a was 3, we had x squared P squared. When our a was 4, we had x cubed P cubed. But there are also missing terms, right? So if we look here, there's no xp. And if we look here, there's no x squared P squared, right? And in fact, in all of these, we never have the case where I equals B. So we want to exclude that. And then looking at the remaining term in each of these, we note that when our a was 2, we had x squared p cubed. When our a was 3, we had x cubed p to the 4th. And when our a was 4, we had x to the 4th p to the 5th. So it seems like this final term is of the form x to the a p to the a plus 1. Right, so putting all this together, what we had conjectured at the time, but now is now proven, is that when b is less than a and they're non-negative integers, and p is the set of Dyck paths whose upruns avoid lengths in ar plus b, then p is equal to the sum from k equals 0 to a minus 1, where k is not equal to b, of x to the k p to the k plus x to the a p to the a plus 1, where p equals p of x is the weight enumerator of p. And because of the involution that I defined before, if we can prove this for this set of for this restriction on uprun lengths, then we are also proving it for the same restriction on downrun lengths, right? Okay, so what we want to do is we want to construct some sort of bijection that gives us the grammar that we want. So to do this, we began by looking at some of the simpler cases to see if we could find a pattern on how to prove this. So when we were avoiding upruns of length 2r plus 1, we got that p is equal to 1 plus x squared p cubed. And we're saying that our family p satisfies the grammar p equals the empty path union u squared pd squared p, right? So here, any element of our family is either going to be the empty path, or it has to start with at least 2 upsteps, because we're avoiding upruns of length 2r plus 1, so it can't just start with a single upstep. And then we know that at some point we return to height 1 for the first time, and at some point we return to height 0 for the first time. But there can be stuff going on in these spots, right? So because of the way that we define our D, we know that all these subpaths have to be Dyck paths, right? And almost every uprun in these subpaths are upruns in our overall path, right? With the exception of the initial uprun. But since we're only adding 2 upsteps to the initial uprun of this first subpath, we know that mod 2, it has the same length. So therefore, a path generated by this grammar is an element of our family if and only if all of these subpaths are also elements of our family. And so this, so then we have that this generates any element of our family, and it only generates our elements of the family that we're looking at. And then for those avoiding upruns of length 3r plus 1, we had the output p equals 1 plus p to the 4th x cubed plus p squared x squared. And again, we have that p is either the empty path, or it can start with exactly 2 upsteps, in which case it starts with UUD. At some point, it returns to height 0 for the first time, and there can be some subpath here and some subpath here, where both of these subpaths have to be Dyck paths because of our D. And also, any uprun in these subpaths are upruns in the overall path, and so they have to be elements of our family. And then for this case, right, I mean, the other uprun length that we could have it start with is something greater than or equal to 3, right? And then at some point, it has to return to height 2, height 1, and height 0 for the first time, and we can have some subpaths occurring in these spots. But again, all these subpaths have to be Dyck paths, and almost every uprun in the P subpaths are upruns in our overall path, the only exception being this initial uprun, but since we're adding 3 upsteps to it, we know that mod 3 is the same length as the initial uprun of this first P subpath, and therefore we know that all of these P subpaths do in fact have to be elements of our family, right? So then we know that this grammar holds. And now that we looked at some of the more basic examples, we can go on to the general case. So basically what we were doing, right, is we were dividing P into subfamilies based off of the lengths of their initial upruns. And this allows us to ensure that we're not double counting anything, right, in our grammar. So if the length, so one option is that the length could be equal to k for some k between 0 and a minus 1. in which case it has the grammar u to the k, dp to the k. And here we're going to have the ith d denote the first time that the path returns to the height k minus I after that initial uprun. So here it's clear that every uprun in the p subpath is an uprun in the overall path, right? And then we also want to make sure that we include the empty path, which corresponds to the case of when we have our k equal to 0, right? And then we know that when k is equal to b, the set of paths in our family is the empty set, right? Because we can't have upruns of length ar plus b, which means we cannot start with an uprun of length b. So we know that this grammar will generate all of the elements of our family that start with an uprun of length k, and that we're excluding the case k equals b. All right, so otherwise, it's going to start with an uprun of length greater than or equal to a, in which case it's going to have the grammar u to the a, p, dp to the a, where our d's again are denoted as the first time that the height returns, the first time that the path returns to the height a minus I after that initial uprun, right? So then they're all Dyck paths, and almost every uprun in these subpaths is an uprun within the overall path, with the exception of that initial uprun, which is u to the a plus the initial uprun in that first subpath. So mod a is going to be the same length. Okay, so then we can put all this together, right? And we get that p is equal to the union from k equals 0 to a minus 1, where k is not equal to b, of u to the k dp to the k union u to the a p d to the a p. And then we can translate this into our polynomial equation and see that this does in fact match the equation that we had in the statement of our theorem, right? And so that concludes our proof for this. All right, so then we just looked at the case of A is specifically greater than B. So then next we consider the case where A is less than or equal to B. And here we got that P plus X to the B, P to the B, is equal to the sum from K equals 0 to A minus 1 of X to the K, P to the K, plus X to the A, P to the A plus 1. Oops. Okay, and to prove this, we were going to show that P satisfies the grammatical equation P union U to the B, dP to the B is equal to the union from K equals 0 to A minus 1 of U to the K, dB to the K, union U to the A, P d to the A, P. Okay, so I just rewrote the grammar that I just stated on the end of that last slide. Oh my gosh. Okay, so by the same argument as the previous proof, I'm not going to go over this in detail because it's the same exact argument. We know that P is generated by the right-hand side. However, it is not true that the right-hand side only generates elements of P. So this first part is fine, right? Because we know that U to the K is of an acceptable length. And then we know that any uprun in a P subpath has to have a appropriate uprun length. Otherwise, this wouldn't be a subpath in our family. So we need to look at this. But here, right, we have that any uprun in the P subpaths with the exception of the first P subpath is going to be an uprun in the overall path because they're all preceded by a downstep. So if an issue occurs, it has to occur with the uprun length of the initial uprun, right? And in fact, this only happens if that first P subpath in U to the A, P d to the A, P starts with an uprun of length exactly B minus A, right? Because we know that this has a bad uprun, initial uprun length if it has an uprun of length AR plus B for R greater than or equal to 0. But we know that this P subpath can't have an because it's a member of a family, can't have an uprun of that length, right? So therefore, it has to have an uprun of length B minus A. Okay, so if this is the case, we can take our path, our overall path P, And it's going to be an element of u to the b, w, dp to the a, where w is just that first subpath without the first b minus a up steps. So we just take the first b minus a up steps and push them into our initial up run. But then w is going to be an element of dp to the b minus a, right? So we know that we're going to have b minus a more down steps than up steps, right? So they're not going to be part of any of the Dyck paths, right? Because we took out b minus a up steps already. And we're going to let d be defined the same way as before, where it's the first time that we're stepping down to that height. So we know that whatever happens in between has to be a member of our family. So then putting this all together, right, we just replace the w with dp to the b minus a. We get that p has to be an element of u to the b, dp to the b. And so that's why we wanted to include it on the left side of our equation, right? Because it's generated by the right-hand side, but it's not an element of our p. So that concludes the proof of that theorem. Now we're going to consider the case of when r is a positive integer, and we're looking at the set of Dyck paths avoiding upruns and downruns of lengths 1 to r. And here we got that p plus xp is equal to 1 plus x to the r plus 1p plus xp squared. And so to find our bijection, we again want to divide our p into subfamilies based off of the length of their initial upruns, and this allows us to make sure we're not double counting. So one option is that it begins with an uprun of length 0, in which case it has to be the empty path. It could also start with an uprun of length exactly r plus 1, in which case it has to have the grammar u to the r plus 1, d to the r plus 1, p. Right? So we know that if it starts with an uprun of length exactly r plus 1, then that uprun must be followed by a down step, but we can't have a down run of length less than r plus 1, so it has to be followed by at least r plus 1 down steps. And then we can't step down again because then we'd be at a negative height. So that's how we know that it is exactly r plus 1 down steps. And then whatever happens after has to be a member of our family, because we know that we can't go below height 0, and we have to start and end, and we have to end at height 0. So that's how we know that any element of our family that begins with an uprun of exactly r plus 1 needs to be generated by this grammar. And that also this grammar only generates members of our family that start with an uprun of length r plus 1. Okay, so otherwise, the path has to begin with an uprun of length greater than r plus 1, in which case it has grammar up dp, right? And here we have d marked the first time that our path returns to height 0. And here we have that almost every uprun and downrun in our p subpaths is an uprun or downrun in the full path. In the initial in the initial p subpath, however, the first uprun and the last downrun are one step shorter than their corresponding runs in the full path. But since we know that our overall path is starting with an uprun of length at least r plus 1, we know that if we're writing our path this way, right, that this first p subpath has to start with an uprun of length at least r plus 1, since the overall path started with an uprun of greater than r plus 1, right? And then we also know that it has to end with a downrun of length at least r plus 1, because we know that we're ending at the same height that we started, right? And that the upruns in between, since the upruns in that path that aren't the first uprun or upruns in our overall path, we know that the uprun preceding the last downrun must have a length of at least r plus 1. So in order to return to our starting height, we have to go down at least r plus 1 up steps, right? Okay, so that's how we know that this subpath does in fact have to be an element of our family P, and by the arguments that we've been using a lot, so does that last P subpath. Okay, so that shows that this grammar generates any element in our family that begins with an uprun of a length greater than r plus 1. However, an issue occurs if that first P subpath is the empty path, right? Because then we have UDP, and we have an up run of length 1 and a down run of length 1, both of which are not allowed. But this is the only time that we're going to produce anything that is not in our family, right? Because otherwise, we're just extending an already long enough up run and an already long enough down run. So all of our up runs and down runs will still have an appropriate length. So putting this together, right, we had that P was generated by the empty path union U to the R plus 1, D to the R plus 1 P union UPD. And then we want to include the UDP on the left-hand side because that is an element generated by the right-hand side that is not in our family. So then we can translate this into the polynomial equation that we stated in our theorem, and that concludes the proof of that theorem. All right, so then we considered for positive integers m and n, where we're avoiding up runs of length 1 to m and down runs of length 1 to n. And here we got that p plus xp is equal to 1 plus xp squared plus x to the max n m plus 1 times p to the 1 plus the absolute value of n minus m. And note that we already showed the case of m equals n in the previous theorem. So we can assume that m is greater than n because of the involution that we defined in the beginning of the presentation. We know that if we can prove it for m greater than n, then we can also prove it for n greater than m because we're just switching the restrictions on our up runs and down runs. So if m is greater than m, right, if m is greater than n, then we want to split up p based off the length of the initial up run again. And so again, we have that if the length is 0, it must be the empty path. If the length is equal to m plus 1, then it has to have the grammar u to the m plus 1, d to the m plus 1, pd to the m minus n, p. So we know that that initial up run has to be followed by at least n plus 1 down steps, and that the ith d, as usual, denotes the first time that we return to the height m plus 1 minus I, which ensures that each of these subpaths are in fact Dyck paths. Also, the last down run in each subpath must at least be as long as the up run preceding it. So if as long as these are any of these subpaths that are non-empty, will end with a down run of length at least m plus 1, which is going to be greater than n plus 1 because m is greater than n. And so that ensures that these all do in fact have to be elements of our family. And so this grammar generates the members of our family that start off with length equal to m plus 1. Okay, so then otherwise the length can be greater than m plus 1, in which case we have the grammar UPDP again, where d denotes the first time that the path returns to height 0. And by the same argument that we used in the previous proof, we know that there's an issue where the first p subpath is the empty path, and we get UDP here, and it's the only time that this will produce something that is not in our family. And so here, putting this all together, we have that p was generated by the empty path UPDP union u to the m plus 1, d to the n plus 1, p d to the m minus np. And then again, on the left-hand side, we need to add in the UDP that was counted by the right-hand side, but not the left, but not in our family. So then we can translate that into our polynomial and get the polynomial that we wanted from our theorem. So that proves the case for m greater than n, and by our involution also proves the case for n greater than m. Okay, so finally, we looked at the case where r and k are positive integers, and p is a set of Dyck paths avoiding up runs of length 1 to r and down runs of length k plus 1 to r. And here we got that p plus xp plus x to the r plus 1 p to the r plus 1 minus k is equal to 1 plus xp squared plus x to the r plus 1 p plus x to the r plus 1 p to the r plus 1. So again, we're splitting up our p based on the length of its initial uprun. And as always, we have that if the length is 0, then it's the empty path. If the length is exactly r plus 1, then it has the grammar u to the r plus 1 dp to the r plus 1, where again, the ith d is the first time the path returns to height r plus 1 minus I. And again, we have that the last down run in the P subpath must be as long as the up run preceding it, right? So basically, and then any up run in these P subpaths are also up runs in our overall path, right? So basically, right, we know that it has to end with a down run of length at least r plus 1. So that's how we know that these must be elements of our family. And then also, right, note that if the first KP subpaths are the empty path, then our grammar gets rewritten like this, right? And here an issue can occur because we don't want a down run of length k plus 1 to r, right? So if all the P subpaths except for the last one are empty paths though, then we get u to the k plus 1 d to the r plus 1 p. And that's fine, right? Because we have a down run of length r plus 1, and that is allowed. And so, but any case other than that, right, we would have a down run of length somewhere between k plus 1 and r. And so that's going to be a forbidden length. And we know that this is going to be the only time that we generate something that is not in our family, right? Because otherwise, whenever you have your first non-empty P subpath, you're just adding down steps to it. And so since this already ends with a down run of length at least r plus 1, we know that we're not going to create any other bad down runs. So if a down run that is not allowed occurs, it has to happen before our first non-empty P subpath. Okay, so then otherwise our first up run has to have length greater than r plus 1. And again, we have the grammar up dp, where d is the first time that the path returns to height 0. And as with the previous few cases, there's only an issue if that first P subpath is the empty path and we have UDP, because then we have an up run of length 1, which is not allowed. So then putting this all together, right, we had that P was generated by the empty path, U union, UPD union, U to the R plus 1, DP to the R plus 1. But that also generated UDP, which is not in our family. And then we also got U to the R plus 1, D to the K, DP to the R plus 1 minus K, which includes elements that are not in our family. But since U to the R plus 1, D to the R plus 1, P is both a member of our family and a member of this grammar, we need since we double counted it on the left-hand side, we need to double count it on the right-hand side as well. And then from there, we can translate it into the polynomial equation that we stated in our theorem. And so that proves the theorem that we stated. Okay, so in conclusion, basically what we did, right, was we provided grammatical proofs of combinatorial results and found infinite families of grammars. So we extended Zeilberger's findings on a specific set of restrictions to the infinite families. And another reason that the grammatical proofs part of our paper is so significant to our paper is because it provides structural information that's not given by automated proofs, because you can really see how you build the elements of your family recursively. So further things that you could look at, right, are what other things can we enumerate using these sorts of grammatical proofs, like other paths or even other restrictions. Like, could you do this with more complicated restrictions, such as the paths avoiding upruns, where the next upruns that have like odd length, where the next uprun will be of even length. So if you don't allow things like that, then is there a way to also do similar grammatical proofs and things like that? Yeah, and that's the end.
All right. Well, thanks, AJ, for that very interesting talk.
Thank you.
Are there questions or comments?
Eric, I had a comment. Actually, you asked a question earlier about a bijection between certain Motzkin paths and something else.
Yes.
It was between Dyck paths that avoid upruns of length 3 and Motzkin paths, right?
Right.
So there is a bijection. If you take every UUD, so 2 upruns followed by a down, replace it with a single U, and then every remaining up, down, replace it with a right step. I forget what letter we used for that. So if
Okay.
you think about it for a minute, this ends up being a bijection.
Nice. All right, cool. Thanks.
That's not due to me, though. Someone in the OAS did that years ago.
Ah, okay. Other questions or comments?
I have a question in terms of like motivation for considering particular restrictions on Dyck paths. Like, why is it like because it's easier to do like this linear type of restrictions on up and down, or is it like motivated because it has interesting applications?
Well, it's definitely easier. Yeah, I'm not really sure why we decided to do these specific restrictions. I think it's just like we played around with other sorts of restrictions, but these were like the ones that we had found most of our, findings on. And then, yeah, I mean, we basically just stuck with it for our paper because to make it like more cohesive, I guess.
Yeah, it's kind of amazing that the polynomial equations come out so nicely
Yeah.
for this particular pattern. So yeah, that's a really nice result. Do you have any sense if you change the AR plus B to something, like AR squared or something like that, will that completely ruin the algebraicity of these sequences?
So I know that's something that like Robert and I had talked about. I think that we just decided that it was beyond the scope of like what we could do.
Sure.
I think there's
Right.
some computer science theorem that tells you should not expect a nice generating function if you don't have a linear restriction. Like
Okay.
there's a theorem that classifies what kinds of things context-free grammars can generate, and putting a square in there suggests that no, you can't do that. So it probably ruins it, sadly.
Okay.
Speaking of motivation, a quick comment. The initial stimulus came from Professor Vladimir Volodya Retach, in which it came up naturally a specific kind of question in his study of non-commutative linear algebra. So he came up with multiple paths. So that was the initial motivation that led to the beautiful work of Robert and AJ.
What is the name of the professor again, like you mentioned?
Oh, right, good. Vladimir Retach, a close collaborator of the late Israel Gelfand. He wrote lots of papers.
Thank you.
He's my colleague.
Anything else?
Yes, I would like to do the question. Is it possible to use this grammar approach to study another kind of lattice path whose generating function is non-algebraic, or you always find algebraic generating functions with this approach?
I have no idea.
Okay.
Yeah, I guess the context-free grammar will always give an algebraic generating function. Is that right?
Yeah,
Ah,
it should,
okay.
right? Yeah.
Okay.
So yeah, I think
If it's ambiguous, if it's non-ambiguous, that's the technical thing.
Yeah.
All right, well, let's thank AJ again for a great talk.
Thank you for having me.